Okay, hi Maths pals. We are looking at applying vector calculus, the first video, and looking at vector equations of motion. From your regular calculus class, we know that we have a relationship and we can move from one of these quantities to the next. That you see in front of you, the three quantities are displacement, or sometimes referred to as position, velocity, and acceleration. In order to go from one to the other, we apply calculus. So if we take the derivative of displacement or position, we get velocity. So the process is called differentiation. And to go from velocity to acceleration, it's the same process. It's repeated on the function for velocity. So I'll just write an abbreviation there. If we go back the other way, if we give an acceleration in order to go back and yield velocity, we integrate. So we use integration or anti-differentiation. Likewise, velocity to position. So it's anti-differentiation. So letting you know where we're heading here, you should get these equations down. Pause the video and write them down. And I'd just like to add that we're going to look at these, and these are vector valued functions, and we can see the process of, well, in this image here, you can see the process of differentiation going from the quantities in each of the components I, j, and k. And it's implied that there's anti-differentiation going back the other way. To explain all this, we're looking at vectors describing motion. So here we go. Here's the lowdown. So the position vector, which you are familiar with from previous work, r of t, where it is a vector quantity r. In two dimensions it's x of t I plus y of t j in two dimensions, and we can extend it to 3. The velocity vector is v of t. Notice the tildes, I'll use tildes or boldface, and it's the derivative of r of t with regard to t. It's also got the notation commonly used That's a commonly used notation there. So it'll be the derivative of the vector here, which we'll show soon how to do that. We've got an application of this vector for velocity is speed. Now speed is the magnitude of the velocity vector. So we could say it's the magnitude of this or we could say the derivative of position vector, take the magnitude of that. Acceleration, we call that a of t, and it is the derivative of v dt, or you could say it's the second derivative of r dt. So d squared r dt squared. It's also written as r double dot, noting the second derivative. And sometimes we're asked to take the magnitude of the acceleration, so it's just like the what you see above. Now remember, for this one here. And remember, when we're taking the magnitude of things, okay, so the speed being the magnitude of a vector, so it would be the magnitude of So you see the dots above the x and the y, that means it's referring to the derivative of the position now, where x and y come from the position vector. So really we find the magnitude using Pythagoras' theorem, and if we have 3 dimensions, we extend that out using the given x, y and z from the original equation we drew up there. So now we see what we had here before, and essentially we just take, to go from the process involved, and I'll show some examples in a minute, to go from r of t in a vector valued function where t is a parameter, for the I component x of ti, we take dx dt and it's linked to the operator I. Then for the acceleration from the velocity, we take the second derivative, or we just take the derivative of the middle, which is velocity, and then we follow the same process with y and z of t to get your j and k components. Here's a fairly simple example, and it's just in 2 dimensions, and a lot of the questions are, not all of them are in 3 dimensions. So we've got to find the velocity vector and the acceleration vector based on the position vector given. So finding this here, r dash of t, or r dot of t, or the velocity, we take the derivative of the 20t with regards to t. So as you get better at this, you won't need to write this first step down, but for now it's the derivative of 20t with regards to t in the I direction, and likewise for the j direction, so it's the derivative with respect to t of 15t take 5t squared, using the mathematical methods you know already, and that would be 20, the derivative of 20t with regard to t is just 20, so it's 20i, and for this next one, take derivative of each, so we have 15, I'm going to put it in brackets to group it together, minus 2 by, I won't write that. If you're watching this video, you should know, you'll be able to do this in your head, so not 2 by 5, just go 10t. Now please group that together because it's all j. Okay, so that's r dot t. So the second derivative, we use the interim result above, so we're finding the derivative. So that'll be the derivative of 20 with regards to t in the I direction, plus derivative of 15 minus 10t with regards to t. And again, as you get better, you won't really need to write this step, but it is explaining as you're learning. And the derivative of a constant is 0, so it's 0i, and the j's, we have the 15 comes out as 0, so we've got negative 10j, the t goes to power 0, so it disappears essentially, and we've got negative 10j. So in some models that might be, if we've just got 2-dimensional motion, for example, that might describe some quantity going straight down, like gravity. Okay, so the acceleration is straight down by negative 10 units, but that's further down the track. Okay, so that's a simple example there. Okay, here's a mid-level example, perhaps. A particle with a position vector given there. It's 3 dimensions, and it's deliberately done there to give your differentiation a little bit of a workout. Hopefully you're familiar with there's a cubic there, there's a sine function, trig, and then there's a base e exponential, So hopefully you've looked after your calculus, okay, before now. So we have to determine the velocity and acceleration vectors, and t is at least 0. And by the way, sometimes for these little these little vectors, basically not position vectors, these basically the unit vectors I, j, and k, sometimes you'll also see them written with the little hat like that too. Okay, so just throwing that in there, sometimes you see that. So to get the velocity and acceleration vectors, let's go for the velocity one, r dot, and we basically find the derivative with regards to t of each of those three components there. This time around I'm not going to put in the that d dt working. I'm just going to do it because that's assumed knowledge by now that we can do that, except for perhaps on some more difficult functions. So the first one will be 3t squared I. The second one is a simple application of the chain rule, or perhaps just learning a rule. 18 cos 3t. And that's in the j direction. Now we've got another chain rule there, so we've got a negative going to be in minus 6 e to the t over 2 k using the chain rule. Okay, continuing on now with the acceleration vector, we have 6t in the I direction minus 54, so I'll be naughty and I'll scribble that out because the derivative of cos is negative sine, so minus 54 sine 3t in the j direction, and for k goes back to positive there, and 3e to the negative t over 2k. Now at the beginning of the video you saw the flowchart talking about differentiation and anti-differentiation, and so looking at the integration of vectors, the anti-differentiation side, we can show some examples too which show that in motion, that's a pun, we show that happening. We do have to take into account the constant of integration, and the constant of integration we could just call c is actually a vector quantity as well. It's interesting. Rightio, so integration, we've got given r dot t, or the velocity, and it is 2i plus 6tj, where t is at least 0, and r, now this is a specific value, notice that there, r1, r of 1, which is 3i plus j. Now, very important to realize that this is no accident. You need two pieces of information in order to get these out, otherwise this will be indefinite. Okay, it'll be indeterminate and we won't be able to work out the c. So two pieces of info. Now that's often it's r of 0, but not always. Like in this one here, it's r of 1, and might be r of 2 or r of anything. Okay, so a specific condition is given to you, so you need that so you can work out the constant later on. Okay, and then that gives us the full, we need that for the full r of t position vector. Okay, so tally-ho and off we go. So in order to get r of t, we have to integrate r dot of t. So we'll write that down. It's important to know. And remember, it's with regards to t. The modus operandi is very similar to the differentiation of vector-valued functions. We integrate everything in regards to t as we go through the terms for I, j, and k. So let's do that. So we have the integral of 2 I dt, or 2 dt, integral of 2 dt in the I direction more correctly, and we have the integral of 6t dt in the j, and of course this can work in 3 dimensions as well, but this one's just 2-dimensional. So we get that, and of course we get a constant. As I said, the constant is a vector quantity, so we put a tilde under the c, and this is where we make use of the magic extra bit of information that we saw up there. So we apply the information r of 1, so let's do that, and we use these two lines in tandem. So for r of 1, we know that you can get it by subbing 1 into this equation. So let's do that. We'll call that the left hand side. So that'll be 2 times 1, which is 2, plus 3 times 1 squared, which is 3, plus that constant that we're trying to find, and we know that that's equal to 3i plus j based on the given information. And what we can do then is, I've just made these symbols up, but they make sense, and really the vector c will have an I and a j component is all that's really saying. So I've just given them some symbols there, and here we go. So on the left hand side we're going to split this fellow up into this. So let's do that, this, that. Alright, so 2 plus c sub x I plus 3 plus c sub y j equals 3i plus j. So equating components, you'll be able to do this more quickly after you've practiced some. When we equate components, we can drop the temporarily drop the i's and the j's. So 2 plus c sub x equals 3. That means c sub x is pretty easy to find. It's 1. Same with j. We've got 3 plus c sub y equals 1, equating the components. Okay, and that means c sub y equals -2. And yay, therefore c is 1i minus 2j, or I minus 2j. Right, so putting the constant of integration in there, the vector c, I'll put that at the end. So what we do now is actually put the I components together. So we've got 2t and we've got 1 here, so 2t plus 1 I, and then the j components, so we've got 3t squared minus 2 there, and there's our vector. Okay, now for a more advanced one to finish off the video. So we are given acceleration in this one, and it's 6t I. We have to determine the position vector, and because it's got 2 stages in it, so integrating to get back to velocity and integrating again to get back to position, we're given 2 of those specific vectors there to deal with the constants in each case. So let's find the velocity first. So r dot is what we're after, so we have to integrate r double dot with regards to t, and we do that as such. It's only got a single dimension, and we've got 3t squared I plus the constant vector Now it's going to be 2, so I'm going to call that C1, C sub 1, that vector. So given that r dot of 2 is 6i minus 3j, we can sub that into this temporarily indefinite equation for r dot 2. So on the left hand side we have 3 times 2 squared, which is 12i, plus c sub 1 will equal 6i minus 3j, the given information. So we can work out the constant vector, negative 6i minus 3j, and then now we can put together the vector for velocity in full using what we've learned earlier on in the video. It's an I, I'm sorry, it's not writing for me. And we get 3t squared takes 6i minus 3j. So we're, well, more than halfway there. We've found the first of two things, and it'll go a little bit quicker now. So, a little bit, not hugely. I'm just being optimistic. So, finding the integral of the velocity in order to get the displacement vector. Same process. Okay, so like last time we do that, and then we take the integral, and done like so. And now we have to use the given information for r of 2. Okay, so we're using r of 2 to help us out, and we've got on the left hand side using what we have in the previous line there, subbing in 2, so subbing all that in, okay, like that, and equating I and j components again. Okay, the same process as we did a step earlier, and you can see that there, and we've got C2 is 8i plus 4j. Just to save some time, we didn't write that intermediate step there, and grouping them together in I and j components, we have our position vector.